And we're back. It's Professor Tabs here. We're talking now about the highlights of congenital immunodeficiencies. So before we talk about the immunodeficiencies, let's think about the maturation of B and T cells. What can go wrong in the life cycle? Remember that during their maturation, B and T lymphocytes go through cycles of proliferation and expression of receptor chains by gene recombination, and that cells that fail to express the useful receptors die by apoptosis because they do not receive the necessary survival signals, and that at the end of the process the cells undergo positive and negative selection, and the lymphocytes shown may be B or T cells. So I'm looking at a picture in front of me, and you can't see this picture, but I'm just going to summarize when it is that things don't go well and the cell dies. So what is positive selection? Well, positive selection basically is when the T cells interact with the MHC, and it's a test really to see if the T cells are correctly interacting with the MHC, and if they do not interact well, then that T cell will then die and not mature, and if they do, then they are given the signal to survive. Now, the negative selection is a question of how well they're able to bind with the self-MHC peptide. And if it's too strong, then they would die, obviously, because this will result in autoimmune diseases, for example. And so we have positive selection and negative selection. Positive selection being how the T cells interact with the MHC, and negative selection being how capable they are to bind with the self-MHC peptides. And I want to put a shout out here right for how I learned about these. In addition to my med school classes, I learned a lot from Fast Track USMLE, so if you have a chance to download those videos, they are fantastic. Okay, so let's just touch a little bit on the congenital immunodeficiencies caused by defects in the lymphocyte maturation. First, I'll give an overview, then I will describe them in more detail. First, let's talk about B cell maturation. So we have a stem cell that then becomes a pro-B cell that becomes a pre-B cell, and if things go well, they become an immature B cell and then a mature B cell. So along the way, if things do not go well, you might develop X-linked agammaglobulinemia. And so in this case, the pre-B cell would not become an immature B cell. And so then this would be a problem. So you'd have X-linked agammaglobulinemia. And how about for T cell maturation? Remember, we have a stem cell that becomes a pro-T cell that becomes a pre-T cell, then a double positive immature C cell. A double positive immature T cell is when it is both a CD4 and a CD8 cell, and then it becomes either one, a single positive mature T cell. So in this case, for the T cell maturation, there might be X-linked SCID, or you might have a lack of a thymus. This would be DiGeorge syndrome. Now, right in the middle here, you have affecting B cell maturation and T cell maturation is ADA or PNP deficiency, which is also known as autosomal SCID, and also RAG deficiency or autosomal SCID. And this affects both B cell maturation and T cell maturation. So then let's ask the question, what are severe combined immunodeficiencies or SCIDs? We just talked about above the SCIDs that can affect both B cell and T cell maturation, ADA, PNP deficiency, and RAG deficiencies. So let's discuss what they are. So severe combined immunodeficiencies, these are disorders that affect both B cells and T cells. And this results in humoral and cell-mediated immunity defects. And unfortunately, children with SCID usually have infections during the first year of life and succumb to these infections unless treated. So what are congenital immunodeficiencies are caused by defects in lymphocyte maturation. So here we're talking about X-linked SCID, and this is caused by mutations in the cytokine receptor. So here we're talking about T cells. So as for T cell maturation, think about X-linked SCID. Don't get that confused with B cell maturation and the X-linked agammaglobulinemia. And then we have adenosine deaminase deficiency, or ADA, and purine nucleoside phosphorylase, PNP deficiency. And this leads to accumulation of toxic metabolites in lymphocytes and a decrease in T and B cells. So this is affecting both the T and B cells. So as a quick review here, we have the ADA and PNP deficiencies affecting T and B cells. And as for the T cells, we have the X-linked SCID. And for the B cells only, it is the X-linked agammaglobulinemia. So more about congenital immunodeficiencies caused by defects in lymphocyte maturation. RAG deficiency. RAG deficiency is a defect in antigen receptor gene rearrangement, which leads to an absence of mature B and T lymphocytes. So here we do not have mature and B and T lymphocytes. So remember, thinking about this RAG deficiency, this is affecting both B and T cell maturation, and this is occurring at the point between pro-B and pre-B and pro-T and pre-T, whereas the ADA or PNP deficiency occurs between the stem cell maturation and the pro-B or pro-T maturation. And as a review, X-linked agammaglobulinemia, this blocks the maturation beyond pre-B cells. So when I say pre-B cells, it means that they don't get to become immature B cells, and of course they do not become mature B cells. So pre-B to immature B cells is where you get BTK deficiency or X-linked agammaglobulinemia. What is DiGeorge system? DiGeorge syndrome. This is a congenital malformation that results in defective development of the thymus. So you would not have T cell maturation. So just as a review, let's remember that for the steps in the activation of T lymphocytes, the responses of T lymphocytes to T-associated microbial antigens consist of a series of sequential steps that result in an increase in the number of antigen-specific T cells and the conversion of naive T cells to effector T cells. And in this change, for example, naive CD4 cells then proliferating into effector cells, the activation of macrophages, B cells, and other cells. What is the cytokine that is involved in the situation? Remember, of course, the cytokines are the interleukins. So the major one here is interleukin 2, which is its principal action is the survival, proliferation, and differentiation of effector and regulatory cells. And this affects CD4 cells, CD8 cells, and T cells. And talking more about the steps in the activation of T lymphocytes, what is clonal expansion? Clonal expansion is the rapid increase in the number of antigen-specific lymphocytes, and this is stimulated by cytokines, and the cytokines, of course, as we just said, is interleukin 2. What is differentiation? Differentiation is the conversion of naive T cells whose function is to recognize microbial antigens into a population of effector T cells whose function it is to eliminate microbes. So let's summarize the secretion of cytokines. Remember that T cell proliferation in response to antigen recognition is mediated primarily by an autocrine growth pathway in which the responding T cell secretes its own growth-promoting cytokines and also expresses cell surface receptors for these cytokines. So here we're talking about interleukin 2R, and the cytokines would be interleukin 2. So it's autocrine growth, and the T cell secretes these cytokines. So the final section here is an MCQ. Which of the following cytokines is most effective at inducing T cell survival and proliferation? A. Interleukin-1 beta. B. Interleukin-6. Interleukin-2 is for C. Sorry, C is interleukin-2. D is tissue necrosis factor alpha. And if you remember before, we talked about the pyogens, fever-inducing cytokines, interleukin-1, interleukin-6, and tissue necrosis factor alpha. Those obviously not the answer. Here the answer is interleukin-2. Thank you very much.